Okay, today we're going to move on to talking about hypothesis testing for variances, and let me get my laser pointer here. There we go. And a couple other things in sections 10.6 and 10.7 that rely on the same concepts. So basically, we've covered means and proportions already. We're adding variances here. We haven't talked about variances prior to this, so this is somewhat new. I'm actually going to go back and cover a little bit from section 8.5 that we skipped up until now. Let's skip some of their text. What we're looking at for variances a lot of times is, in terms of quality stuff, we're after a small variance and if very very little noise around the mean. And so mostly in quality testing, it becomes important. The concepts we'll use here, we use for some other things in the next couple sections, so they're really important. We use the exact same logical algorithm here, though. General steps are state the null and alternative hypotheses, determine which distribution to use, and state the level of significance, gather the data, and calculate anything we need based on it, and then draw a conclusion and interpret the decision. Okay, with variances here, we've got a ever so slightly different set of criteria. You'll remember we had things mostly around whether or not the central limit theorem would apply. Here we've got slightly different criteria. As before, we need a random sample, and in this case, the population distribution needs to be approximately normal. We don't have a minimum sample size as such, anything like that. We just need some sort of assurance that the population distribution is approximately normal. So as a reminder of notation, using the null and alternative hypothesis, they're going to be phrased either in terms of the variance or the standard deviation. Remember, the variance and the standard deviation are related. Standard deviation is either the square root of the variance or the variance is the square of the standard deviation, whichever way you want to think about it. The test statistic we use is the chi-square. Chi-squared is also the distribution we use for this, and I'll cover that in a little bit. This is the stuff I added from section 8.5. And again, as with the student's t-distribution, this is defined using degrees of freedom, sample size minus 1 degrees of freedom. Okay, so the confidence intervals for dealing with variances use the chi-squared distribution, which we'll talk about in a minute. And again, this is not next. This is the Greek letter chi. I believe it's the capital chi. The chi-squared distribution, again, it's defined by degrees of freedom. It is, however, not symmetric. So it's not like the normal distribution or the student's t-distribution. This is not symmetric. It should look something approximately like this. That would be right tailing, if I'm looking at this correctly. So we again have critical values in a table in the back of the book. They are in table G, excuse me, of Appendix A. So that is F. There we go. It's on page 902. And you can see the shape of the curve up there, all of that. And as with the t-distribution, that first column contains the degrees of freedom. So all we really need is the degrees of freedom for there. Across the top row in this, we see some common values for areas on the right of that tail. Excuse me. And the column we use gets a little bit more complicated. Which alpha we want. Let's get to here. So depending on what we're after, we may be using 1 minus alpha, and we may be using alpha, depending on what we're looking for. So this is the value that is to the right of the critical value, just like it is for the normal distribution. It's giving you this area, so that entire column is the 0.95 area, and that's the critical value of chi-squared is going to vary depending on degrees of freedom. Then this is a little unique in how we find the interval estimates and margin of error. We don't have a single set margin of error because it's not a symmetric, which made things a lot simpler with the other distributions we've talked about. We have separate formulas for each endpoint rather than one formula for a margin of error. And this comes from it not being symmetric, as I said. So on one side, the numerator here is the same. Degrees of freedom times the sample standard deviation squared. And this is or you could call this the sample variance. So population variance, sample variance, or standard deviation squared, whichever way you want to look at it. So we've got the critical chi-squared of at alpha over 2 on one side, and the critical chi-squared at 1 minus alpha over 2 on the other side. So if we think about this in terms of here, we'll have, alpha over 2 over here, and 1 minus alpha over 2 over here. So if alpha was 0.1, alpha over 2 would be 0.05. So we'd have a chi-squared sub 0.05, and 1 minus 0.05 would be 0.95, which would give us this chi-squared right here. So back in this table, one side would be this 1.145 for the critical value, and the other side would be right here, 11.070 for the critical value. Okay. Hopefully this will get a little more clear as we use it a bit. And also, hopefully, you can see where this is coming from and why it's a little bit more complicated. Again, we've got sample size, sample variance, critical values on each side. Right. If we wanted to do this in terms of standard deviation instead of variance, we could just take the square root of everything like they've done here. But it's essentially the same calculation. It's just we have a square root as well. Yeah, nothing I want to add for that. Okay, so we've kind of covered the chi-squared distribution in broad terms. Let's move on to hypothesis testing. So for hypothesis testing for variances or standard deviations, we're going to be using chi-squared as our test statistic. Chi-squared is this formula right here. We've got sample size minus 1, sample variance over presumed population variance. as it states here, the presumed value is what we take from the null hypothesis. So as with the other hypothesis testing, it is important to appropriately frame your null hypothesis so that you can do this step. And again, degrees of freedom is sample size -1. You'll need that for finding the chi-squared statistic. In this case, we could have replaced this with degrees of freedom instead. It's just a little clearer not to in some ways. So you can use a rejection region to draw a conclusion, just as we did. I forget which section we first covered that. To find the critical values, we need degrees of freedom, and we need to, again, consider what type of test we're performing, left, right, or two-tailed, just as with the other types. There's this nice handy table. We can reject the null hypothesis if the chi-squared for our sample is less than or equal to the critical chi-squared value down at the lower end, down the left side for a left-tailed test. If it's greater than the chi-squared, the critical value, and on the right side for a right-tailed test, or if it is outside of either of those on a two-tailed test. This is probably a handy chart to make note of and refer back to. As we just saw a few minutes ago, if you look at the degrees of freedom row and the column for the area to the right that you're after, the significance level, you can find your value. So if we're looking at a significance level of 0.05 and a sample size of 7, sample size of 7 would give us 6 degrees of freedom. 0.05 for our significance level gives us a 12.592. Okay, so let's look at an example. Say we work at a pharmacy, we've been buying a drug for high blood pressure. New company says it's got a better drug. They've got the same active ingredient. Maybe company B is generic or something. But they're claiming they're better because the variance in the amount of active ingredient is smaller than with company A. We know that company A's got a variance of 0.009. Sorry, 0009. So what we're claiming then is what company B is claiming is that their variance is less than 0.0009. So this is going to be a left-tailing test, right? We want less than 0.0009. So we've done a simple random sample of 100 pills from the new company, measured the amount of active ingredients. They had a mean of 2.470 milligrams and a standard deviation of 0.026. Is this sufficient at the 0.01 level of significance to support the claim that they've got smaller variance than the original company? Let's assume that the active ingredient is normally distributed, the amount. All right, so step 1, state the null and alternative hypotheses. We did just kind of do that a minute ago, right? Our alternative is that the new company's variance is less than 0.0009. So we can write this mathematically as variance is less than 0.0009. The null hypothesis is that the variance is greater than or equal to 0.0009. Write them as such. Null hypothesis greater than or equal to 0.0009. The same or worse than the existing product. Alternative, what we want to show is that it's better. All right, So we need to know which distribution to use and what the test statistic is and what the level of significance is. Right, we're testing a population variance and we're told we can assume the conditions were met, so we have to use the chi-squared distribution, which is thus the chi-squared test statistic. And we're given a level of significance of 0.01. Okay, let's gather our data and calculate the necessary sample statistics. Got a sample size of 100, variance of 0.026 squared, which is 0.000676, and a presumed population variance of 0.0009. Okay, if we substitute those into the formula, right, there's our sample size minus 1, sample variance, presumed population variance, so sample size was 100, sample variance was 0.000676, and presumed population variance was that 0.0009. We get a chi-squared value of 74.36. As we said, this is a left-tailed test, so the level of significance was 0.01. Degrees of freedom was 99. And if I'm using the table, it skips from 90 to 100. It starts going by tens after 30. Closest value to 99 is 100, so we'll go ahead and use 100. I'm seeing 118.498 for that. What am I doing wrong? I am looking at the wrong column. That's what I'm doing wrong. I need to be looking at 1 minus alpha, so that is 90. So, oh, 0.01, not 0.1. Okay, should be looking at 0.99. There we go. Now it lines up with what I'm seeing here. I get 70.065. So there are some gotchas here. You've got to be sure that you're using the right column here. That for the left-tailed test, you're using the 1 minus alpha. It pays to triple check that you've got the right alpha. That you don't just glance at this like I just did just now and say it's 0.1 instead of 0.01. It is remarkably easy to do. There's a lot of just tiny little details that will get you if you're not careful. So it pays to double check them. And so we have 70.065 as the critical value. So we should be rejecting the null hypothesis if the chi-squared is less than or equal to the critical value. Our chi-squared was 74, which is not in the rejection region, so we should fail to reject the null hypothesis. Right. It helps to look at it down here. The other kind of gotcha is this is not scaled with 0 at the mean. This is scaled from 0 somewhere way down here to off to infinity. It's not symmetric about 0. So 74 is not farther from 0 than 70. It is, well, it's still farther from 0, but it's not farther out the curve, as you can see right here. Okay, so this distribution is a little bit different in that. With the normal or the student's t-test, a 74 would be out here in the rejection region, and you do have to be careful because this distribution is different. So we can't, the evidence does not support the drug company's claim that their variance is less than the other companies. Okay, so if we're working for a golf ball manufacturer and they want a standard deviation that does not exceed 0.08 ounces for their golf balls, One of the quality control inspectors says the machines need to be recalibrated because he believes the standard deviation is, feeling some balls or something. He feels like it's different. There's more variance than that, is what he thinks. So he selects a simple random sample of 30 golf balls, gets the mean weight and their standard deviation, and yeah, he gets a larger standard deviation. But is that a large enough one to be relevant? Do the machines, do they need to look at recalibrating? Um, so at the 0.05 level of significance, and assuming the weight is normally distributed. All right, so what's our null and alternative hypothesis? Well, the inspector believes that the standard deviation is greater than the 0.08 ounces. So the research hypothesis is that standard deviation is greater than 0.08. This is given in standard deviation, so we're using sigma and not sigma squared, because we're testing standard deviation, not variance. Logical opposite is that it is less than or equal to 0.08, so we can state them concisely like so. Null hypothesis is that it's less than or equal to 0.08. Research hypothesis is that it's greater than 0.08. All right, so which distribution and test statistic, and what is our level of significance? Well, again, we're testing a standard deviation, so just like testing a variance, we're told we can assume the necessary conditions, so we can use the chi-squared distribution. So we're using the chi-squared test statistic, and we're given a 0.05 level of significance. Let's gather our data. Sample size was 30. Sample standard deviation was 0.0804. Presumed population variance, 0.08. We can input those into our chi-squared formula. Our sample size, sample standard deviation, presumed population standard deviation. Right. Put all those in, we get 29.291. All right. So we're wanting to show that this is greater, so it's going to be a right-tailed test. So we are using alpha, not 1 minus alpha. For a right-tailed test, it's alpha. Right? So rejection region is chi-squared, any chi-squared greater than the critical value at alpha. Alpha is 0.05. Degrees of freedom is 29. So make sure I'm looking at this right. I get 42.557, which matches. So there's our fail to reject region. There's our rejection region. Our value was 29.291, so we can say that there's not sufficient evidence to support needing to recalibrate the machines, which would probably involve, shutting down operation for a little while, which can be an immediate loss of money as you have to shut things down. Okay, so let's look at a two-tailed test. We have a tree farmer who wants to know how much variance there is in the heights of 2-year-old trees on his farm. So he's probably growing Christmas trees. That's generally accepted by botanists that after 2 years of growth, the heights of this variety of tree measured in feet should have a variance of 16. Okay, those are not Christmas trees. Must be fast-growing poplars or something. Farmer claims that after 2 years of growth, the variance in height of his trees is not 16. He selects a simple random sample of 42-year-old trees and finds that their heights have a standard deviation of 0.2 feet. So we're given this in variance and this in standard deviation. It's important to note that. Is there enough evidence at the 0.1 significance level to support the farmer's claim? Just note for myself, this is 0.1, not 0.01. Make sure I've got that in. Assume that the heights of the trees are normally distributed. Okay, so null and alternative hypothesis. He thinks that the variance is not 16. So the logical alternate would be that the variance is 16. So sigma squared is variance. Alternative hypothesis is that it is not 16. Null hypothesis is that it is 16. So H sub 0 for null, H sub A for research or alternative hypothesis. Which distribution do we want to use? So we're testing a variance, and we're told we can safely assume the necessary conditions. Random sample, the population distribution is approximately normal, so we can use the chi-squared distribution. We'll be using chi-squared test statistic. We're given a 0.1 level of significance. With all that, we can gather our data and calculate the necessary statistics. Sample size is 40, which gives us 39 degrees of freedom. Sample standard deviation is 3.2, and presumed population variance is 16. We can put those into the formula as such. There's our 40, there's our 3.2, there's our 16. You got to be careful to note what needs to still be squared, like the standard deviation up here, and what has already been squared, like the variance down here. It's just small detail that could easily trip you up if you're not being careful. So pay attention and note whether you're dealing with a variance or a standard deviation, and that tells you whether or not you need to square that term in this equation. So we get a chi-squared value of 24.96. Okay, in this case we've got a two-tailed test, so we're dealing with 1 minus alpha over 2, and alpha over 2 is our critical values. The level of significance was 0.1, so this is going to be 0.95, and this is going to be 0.05. Degrees of freedom is 39. Right after 30, the table starts skipping by 10, so we'll use closest value, which is 40. Just double check this, 0.95. Nope, there it is. No, 995. There it is, 0.95. And I'm using 40. So I get 26.509 and 55.758. 26.509, 55.758, yes. So we have this, or this is our rejection region. Our value was 24.96, so we can reject the null hypothesis. And it is likely that the variance in that particular farmer's trees is greater than 16. Or not greater than, is different than 16. There's sufficient evidence that, yeah. Okay. Go.